graph me. Y equals 1/2 the quantity x plus 3 squared plus 2. Gonna write down y equals, it was a x minus h squared plus k. That minus h and that plus k were important. From there, hack h, a, k. I'll even do the parent function. Woohoo! Give me an h. Let's try that again. Give me an h.
3, you give 3 to the left.
That was a little staticky, Nina. What did you say?
Minus. You would move it 3 to the left.
Yeah, it's a -3, so it's left 3. Good, 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 good. Somebody else had it as well. Good. A is 1/2. Means it's gonna grow slower. It's gonna get wider. K is 2. Up 2. I'm going up, up, up. Cool. Good. Y equals x squared. Parent function, not a problem. Next is the h. Y equals x plus 3 squared. And we said that's going to go to the left 3. So we're now here, there, and there. Same shape, just moved to the left 3. Some of you are getting pretty good at this, hopefully. 1, 2, 3, 4, 1. I'm now at the left 3. I'm going to take a look at my amplitude, which was 1/2 x plus 3 squared. So that point didn't change. What was at 1 to the left and up 1, 1 to the right and up 1, those values are now cut in half. So it's going to be here and here, which is going to cause my graph to look wider. All of my y values are cut in half. So if you compared this one and this one, this was moved left 3. This was that amplitude of 1/2. And I probably should have put you into groups, but there's so many people coming in late right now for some reason. 1, 2, 3, 4. I know I'm now going up 2. So what this little point was right here, it has a name. It's called the vertex. It's now going to get moved up 2 to there. And I have this nice wideness still. That's good. Y equals the x squared to the left 3, because it was x minus h. The amplitude made it wider. My y values were all cut in half. Finally, the whole thing gets moved up 2. I like it. I love, oh, sorry. Good. Nobody talks to me. I have to talk to myself. I have to entertain myself. Some of you talk to me. Radhika talks to me. Nina talks to me. A couple of others. Okay. Good. Moving on. Shooby-dooby-doo. So we're just still talking about graphs. We're beating graphs to death. No, we're learning everything we can about graphs. And section 2.7 talks, this is going to be one of your easier section, but it talks about some different ways of looking at graphs. And one of them is the symmetry for a graph. And this first part, you know, we can look at the graphs themselves and we can talk about the symmetry. And there's a bunch of different ways to figure out if it's symmetrical or not. And we're going to start with that, but we're also going to make sure we look at the graphs to understand the symmetry. So if it's symmetrical over the y-axis, what? Okay. So let's take a look at a graph. If I have a point 3 and I have a point -3, and this is at 1 and this is at 1, those 2 points are symmetrical over the y-axis. So if I took it, went and flipped it over the y-axis, I would be good. So when we talk about symmetry over the y-axis, we're going this way. If I took a look at this point here, 1, 1, and this point, 1, -1, we have symmetry over the y-axis. And again, this could be more than just a point, and that's what we're going to work with graphs. So all points on the graph. But if I have a y value that's a positive and a y value that's a negative, that's the symmetry over the y-axis. If I have an x symmetry over, I'm sorry, there's the y, here's the x. The last one is, let's say I have the point 2, 2, and now I'm going in pencil, and I take the opposite, that's actually 3, 2. If I take the opposite of the x and the opposite of the y, so instead of the point right here being 3, 2, I have the point -3, -2. That's called symmetry over the origin. So again, taking a look at this, the x were opposites and the y were opposites. When I had this guy in blue, I had the point 3, 1 and the point -3, 1. The y's were the same, symmetrical over the y-axis. Here, the x's are the same, symmetrical over the x-axis. So just a little terminology to get started with what's going on here. And we can take a look at y-axis, x-axis, or the origin by doing these things. If I put -x in for x, I now have the equation y equals -x cubed. And if I cube that and clean it up, I get y equals -x cubed. Y equals -x cubed. So what we're saying here is that we know the graph of y equals x cubed. And this guy are opposites. So this is over the origin. Because I can't flip it over the x-axis. I can't flip it over the y-axis, but it's a rotation. Yeah, I know. Hang in there, folks. This time, if I put in -x, y equals -x squared plus 5, which gives me y equals x squared plus 5. I'm back to what I started with. And you know from a graph of this, I know what y equals x squared looks like. My k is 5. 1, 2, 3, 4, 5. What's that guy going to be? He's going to be over the y-axis. We're gonna make this a little simpler here in a minute. This guy is a circle. Yeah, that's a circle. With center at 0, -1. And I have the whole 4 cut in half is 2, 2, 2, 2. There's my circle. I keep answering my own questions, but does this have symmetry?
Yes.
Over what?
The y-axis.
Yeah, this is again over the y-axis. Well, these guys that are symmetrical over the y-axis, right here and right here, these guys are called even functions. So if it's over the y-axis, it has the name of an even function. In fact, this guy as well, we know what the absolute value looks like. But if I shift it down 2, I'm going to have another even function. So anything over the y-axis is an even function. Anything over the origin is an odd function. And the easiest way to remember an odd and even function, check out the exponent, y equals x cubed. So if I ever want to say, oh, what's an odd function? Y equals x cubed. Okay, so now I'm going to start with those two. Y equals x cubed. Okay, y equals x squared. These are the simplest odd and even functions. Oh, ever. No, even an odd. These are the two simplest ones. Now, here's what happens with an odd function. And this is what we were kind of talking about, and I'm going to make it a little clear. If I say 1 for x, you say what's 1 cubed?
1.
1. I say 2, you say
8.
8. I say -1, you say,
That's still -1.
I say -2, you say
-8.
-8. Very good. So here's what's happening with an odd function. If I take an x and plug it in, any x, right? And if I plug it into my function, but if I take -x and plug it into the function, how are the y values related? So if I took 1 and cubed it, I got 1. If I take -1 and I cube it, I get -1. How are these y values related? O word. If I plug in 2, I get +8. If I plug in the negative version of that, I get
The opposite.
the opposite, right? So this is where somewhere along in your math world, you saw something that looked like f of x equals the opposite of the negative f of -x. The y value for 2 and the y value for -2 are opposites, so I'd multiply this one by -1. Okay, whenever this is true, if I can plug any x in here, and then if I plug its opposite in, I'm going to get the opposite value for y. Cutting edge excitement. I can see it in your face. X, Y. I say 1, you say,
1.
I
1.
say 2, you say,
4.
I say -1, you say,
1.
I say -2, you say.
4.
What do I know about the y values? If I say x, you say f of x, kind of deal. What do I know about the y values? They are the same.
Always positive.
So f of 2 is going to equal f of -2. F of 1 is going to equal f of -1. Their y values are all the same. So an even function is f of any x is going to equal f of its opposite. Back over here, I say f of 1 and I say f of -1. You're going, well, this one's 1 and that's -1. So in order for them to be equal, I have to negate that side. If I said f of 2, does that equal f of -2? No, I have to negate it. So that's the difference between an odd and an even function. And I'm pretty sure you've all seen it before. It was just a matter of figuring out what it means. Okay, so if I come down to the bottom of this page, and I want to know, who wants to know? Are you Johnny? Right? I want to know if this is even, odd, or negative. Oh, I'm sorry. Even, odd, or negative. So if I plug in negative x, okay, it's going to be even if f of negative x equals the same thing. It's going to be odd if f of negative x equals negative x to the fourth plus x squared minus 2. That's that multiplying everything in here by -1. All right, well, let's see. This becomes negative x to the fourth minus negative x squared plus 2. And if I clean that bad boy up, negative x times negative x times negative x, yeah, that just becomes x to the fourth. Negative x times negative x becomes just x minus x squared, and the plus 2 didn't do anything. And I'm going, woohoo, because it's this guy right here. So f of x, not this guy. You lose. You lose. You still get a participation trophy. No. But f of x and f of negative x were the same. So this bad boy is an even function. So when I graph it, it's going to be symmetrical to the y-axis. Huh. Huh. Holy cow, we have 18 people here. 8 people came in after we started. I'm going to have to update my attendance sheet. Okay, so again, I'm going to do this. Maybe I'll let you do it. If I plug in f of negative x, so wherever x is, I'm going to plug in negative x. I'm going to look at the result. And if it's the same as this, it's even. If these are all opposites, it's odd. If neither of those cases are true, it's just nothing. So let's see, I'm going to have negative x cubed minus negative x plus 3. That's going to equal negative x times negative x times negative x, which will give me negative x cubed. This gives me plus x. This gives me plus 3. So my f of negative x, I'm looking. This is opposite. Great. This is opposite. Great. This is not opposite. So it's not odd. It's not even. It's nothing. Nothing. There's no symmetry to that problem. Oh, man. Plug in negative x. We're hoping for a result that's either the exact same or everything's opposites. Negative x cubed minus negative x. That becomes negative x cubed because it's negative x times negative x times negative x. This becomes plus x. Check it out, Funk Soul Brothers. This is the opposite. This is the opposite. So it's true and true. This is an odd function. It will have symmetry over the origin. Or we rotated it 180 degrees. Picked it up 180 degrees and put it right back down on top of itself. Number 8, what you get? By looking at it, is it over the x-axis? I'm sorry, one more time.
It does have symmetry. I said it does have symmetry, being an odd function.
And it's an even because it's over the y-axis. So if I was to take this paper, that's why it's called an axis. If I rotate it and put it back down, it's perfect. If I looked at an x value, x is right here. If I looked at negative x, that's right here. and I went up, they have the same Y values. Oh. What about this guy? If I looked at an X right there, yep, you're exactly.
Wait, I have a question actually.
Yeah,
For the last one, how come that's not an odd function? Because it's over the origin.
okay. Let's take a look at the Y values. If I say X is here, you see where its Y value is?
Yeah,
If I say negative X, you see where its Y value is. When
yeah.
the Y values are the same, that's that F of X and F of negative X. When the Y values are the same, it's symmetrical over the origin. So I would take this guy and flip it over the Y axis. That would be me taking this paper and going this way. If I had this graph and cut it out, I could fold it over the Y axis.
All right.
Okay, that didn't sound very convincing. All right, so I'm going to take a look at an X value over here. There you are. There's X. If I look at its Y value, I take a look at negative X and I look at its Y value. Yeah, it's not the same there, but if this is negative, then this is going to be positive. So they're actually opposites of each other. And
So is that an
every,
odd function?
yes, it is. Every X value, if I looked at the negative X value, they would be opposites. This is one where I could say 180 degrees like that. And it's the exact same thing as what I started with a minute ago. It is odd because if I take an X and plug it in and look at its Y value, F of negative X's Y value is the opposite. Remember, this is the Y value. This is the Y value. They're opposites. So this guy again is over the origin. That's the term they use, 180 degrees. Okay. I can't write on that. I already wrote all of that. I need a piece of paper. Do, 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 do. Do, 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 do. Do, 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 do. I have a graph. And I start to plot points. Because I think the world of textbooks introduces this the wrong way. Ba, 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 ba. And I said, okay, I have a point, right here. And I have another point, 1, 2 right there, and 2, 3 right there, and another point right there, and another point right there, and so on. And my points are something that looks like that, okay? And this is, the other day we were talking about this, and we said, oh, we could use our calculator. We could plug in all these points, and we could say, yep, here's the line of best fit right there. Okay. And I have this point 1, 2, 3. That's going to be 3, 1, 2, 3, 4. So we're going to say this point right here is 3, 4. And, this is my line of best fit. And this is the point 0, 1. And I said, what's an equation for that line? Okay, not a bad review point. I need, what is 0, 1? As far as my equations of a line, we had y equals mx plus b, which I don't like. I like b plus mx. That was the slope intercept form. And we had the y minus y1 equal to m times x minus x1. That came from slope, because if I put those x's underneath there by dividing, yeah, okay, what can I do? First of all, in both of these, I need the slope, right? So what's the slope? Y minus y over x minus x. Slope. M equals 4 minus 1 over 3 minus 0. I get a slope of 3/3, which is,
1.
go ahead. Question? No question? We're
No,
good?
I was just saying 1.
Okay, oh, excellent. Thank you. So now that I know that, I need to pick one of these equations and I'm gonna go, wait, stop, collaborate and listen. I know what the B is. That's my y-intercept. My B is 1. So I know the equation for this line is going to this line right here. Yep, y equals 1 times x plus 1. Okay, so I know this is the line that's the best fit for that data. And that data is from that data. Oh, this data has a domain from 0 to 3. Okay, it has a domain from 0 to 3 and y equals x plus 1. So if I'm talking about the company and I have all of these points plotted for the company, and this down here might be years. So during the first 3 years, I could predict my, I'm just going to say profit in millions, some kind, by this equation. So if I said, oh, during the first year, what were my profit millions? You'd say, okay, that's going to be this graph up to the 0.34. You know, that's this area right in here. I'm going to use that equation because that's going to predict my profits. Well, the next 5 years, 3, 4, 5, 6, 7, and 8, we had, yeah, that's when the company went out of business. And, you know, I start plotting my years like that. And I say, okay, so that's going to be a different time. You know, after the first 3 years, somebody else came in charge and we went all the way down to 80. You know, I was kind of sad because that's the 0.80 and the company just sort of died. And I could create an equation for that. You know, I could pick 2 points, might as well use 3, 4, and 80. And I could predict another equation that during my domain of after 3 years up to 8 years, I would use that equation. So if I figured it out. Okay, and then maybe somebody survived and the company grew and all of a sudden we start plotting more points that depending on what year it was, what the profit was. But this is called a piecewise graph because it's graphs and, you know, maybe this one went da 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 da, and that almost looks like an x squared kind of thing because it took off. Instead of a line, it was an x squared. So I have to explain this graph in 3 different pieces from years 0 to 3, you know, and this would be how I would find points on the graph using this equation. From years 3 to 8, oh boy, it was a steady decline. And I would, you know, if I wanted to know what the profit was, I'd pick the years and I'd use that equation it's calculated. And then all of a sudden, you know, the company goes batshit crazy and, oh wait, I can't say that. And from year 8 up to year whatever, it might be y equals x squared, da 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 da. Okay, so these are restrictions on my domain, and these are different equations I would use for that. Okay, yeah, because I can't make one graph to work well with all of my data points. Well, that's where these crazy piecewise functions come in. Okay, we're explaining the data points and we're looking at shapes that look like this. And this guy would be, you know, thinking about what we were just talking about. This guy is going to be the years less than 0. This guy would be the years from 0 on. So there's this graph, y equals x minus 1. Instead of giving points and having to figure it out, it's already given to us. And this graph is the y equals x squared plus 1. Okay, so if I said, hey, okay, my year was -1, that's going to be part of this graph. That's going to be when x is less than 0. I plug -1 in. What were my profits? I can plug it in and do the calculations. And get 2. This is an excellent graph. If I go to -1, I can come up and see that it's at 2 as well. So again, I like starting with a problem and here's years and here's profit and all kind of different things. What is f of 5? Well, my x value is
26.
greater than 0. So hang on, my x value is greater than 0.
Oh, 24.
What's, be careful. It's great. So I'm going to take this 5 and because it's greater than 0, I'm plugging it into that equation.
Oh, it's just
to
4.
Just 4. Yeah, it's just 4. What equation does f of 0 get plugged into?
The bottom one.
The bottom one. So it looks like it's -1. Okay. I always didn't like these until I started to understand them with real life stuff. H of 1, what equation does it get plugged into?
The top one.
The first. Looks like it's going to give me 4. Let me know if I screw any of these up. 3 gets plugged into
The middle one.
second equation. 4 gets plugged into got a little
The
equal-
middle one.
Yeah, it's got a little equal sign, so that's going to be it. And 5 is going to get plugged into the bottom one. Looks like I get 9. Oh boy. Graph the function. Ba, 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 ba. Okay, so here's what I'm gonna do. For this first equation in red, I'm gonna say I want 2 values because this is a line. I only need 2 points to make a line. I'm gonna use the points 0. Okay, that's less than 2, and 1. That's less than 2. If I plug in 0, what do I get?
1.
1. If I plug in 1, what do I get? 1.5. Okay, so my red graph is 0, 1, 1, 1.5. And that's all I need to make a line. But I know my line is going to stop and not include the value for 2. What was the value for 2? If I plug 2 in there, looks like I get a 2 coming out. So that's going to be an open circle. Yeah, let's go blue. Values greater than or equal to 2. 2, 3, 4. I plug in 2. -3. I plug in 3. -4. This is a line, so it has a constant rate of change. So if I say 4, you'd say -5. Without even looking, if I said 5, you'd say -6.
Negative 6.
Yeah, because it's going to be that constant rate of change. 2, -3, 1, 2, 3. I know that one's included, so it's closed. -4. Yeah. Oh, there. Whoop, there it is. So again, this is great, but this is better. We actually plotted a whole bunch of points and had to do the work and come up with the equations and get our hands dirty and talk about the domain. That's the good stuff. This is the tip of the iceberg, the generic part of it. But it is what it is. We're okay with that. Any questions? Oh my, I'm gonna briefly look at this one. Briefly, when X is less than 0, it's -1. And I know that's my constant function. So that guy right there is that blue line. And that happens, things level off for a while. And then this would be a part of a negative, another line from 0 to 2. And this would finally be a third line on it. But this was an important piece I wanted to show you. When it's just -1, no matter what X value I pick, the Y value is 1. And we talked about those horizontal lines before. All right, so I'm going to give my voice a break. I want you, not in a pair, just by yourself, see if you can figure out 14 and 15. Take a look at 14 and 15 and tell me what you think. No Fenstermacher today. No, Slade's not here. The first miss. Alexia, that's her 4th. That is not good. Tim Wills is up to number 5. Some of these people don't like coming to my class. All right, I'm looking at this first one. This is called the greatest integer function, and it is the greatest integer less than or equal to X. I'm going to give you another way to look at this if you didn't get it right away. The greatest integer less than or equal to X. So if I said right here, and there's the greatest integer is right there, give it to me in words of a number line. For the greatest integer function, and this is my X, it's always going to be the integer value to the
Left.
Yeah, to the left. I almost said port side. It's to the left. So this makes it a little easier for me when I start thinking of 1.3. What's the integer to the left? Uno. -0.2. What's the integer to the left? -1. 5. And 3. And I'm thinking that this guy may have messed you up, that -0.2. But knowing that it's the number on the left to the number line works great. So what does it look like? If I went to graph it, it would be, all of those would be 0. From 1 all the way up to, but not including 2, would be 1. At 2, it would be 2, 2.1, 2.2, 2.3, 2.4, 2.5, but not 3. So by looking at the pattern, I can now go into the negatives. And again, I said today, we're going to be looking at some goofy graphs. There's a goofy graph. It's goofy. So I don't want the graph of this. I just wanted to see what the graph of the greatest integer function was. All right, not so bad. A new job offer and sales promotion has a base salary of $3,000 a month. Okay. Once a salesperson reaches 50,000 in sales, he earns his base salary plus 4.3 wah, 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 wah. Write a piecewise function. No. Okay, we're not going to do that. You know, you're going to start with something like S of X equals $3,000 a month plus, and now you're going to get into this 4.3% commission on all sales. And we could sit and do it. It would take 5 minutes. But this is not a very good problem. It's not a very good problem, in my opinion. So I don't like it. Continuing with functions, we want to be able to, you know, talk the talk, keep talking the talk. And I think those 3 are kind of self-explanatory. What's really neat is you're starting to get into calculus talk. When you look at these, and, you know, I want to say every f of x2, where x2 is greater than x1 is greater than x1 kind of deal. And it's increasing, okay? I think you got the idea. The y to the right is bigger. But you need to start to be able to see these things because some of you are going on to calculus. Over here, the y value to the right is smaller. As my x's increase, my f of x's decrease. And then, of course, this is what we call a constant function. So using our interval talk or interval notation, this guy is increasing. Well, my y values are bigger. So it's from negative infinity. So my first one is this guy. From negative infinity up to -2, my y values are increasing. From negative infinity all the way up to, and we're going to go 2, but since that's a touch, we can make this a parenthesis or a square bracket. Looks like I have a constant function from -2 to 0. We're talking about the x values. Well, that's a -2. So I need to include it this time. We could include 0 if we wanted. Now it's decreasing from the x values of 0 to 2. So I'm going to go 0 to 2. And now it's increasing again. Union with 2 to infinity. And beyond. To infinity and beyond. To infinity. Take a second and try that next one. Oh, the weather outside is frightful, but the fire is so delightful. So I have something going on up to this point, something going on up to this point. From negative infinity to -3, it's decreasing. Negative infinity to -3, it's decreasing. From -3, oh, it's still decreasing. It's decreasing all the way out to +2. Negative infinity all the way out to +2. Wait a minute. This guy's decreasing the whole time. What a jokester. Negative infinity all the way to positive infinity. Never increases, it's never constant. It's going down. It's yelling. It's yelling. Timber. Thank you. Thank you very much. Ha. Moving right along. We're having such a good time. Some of you are saying, no more, no mas. The pain, no mas. Two terms, relative mean and relative max, or relative minima and relative maxima. And that's going to be this guy right here, a relative max. Okay. All of the y values to the left and to the right are smaller. Here's a relative min. All the y values to the left and to the right are larger. So two new terms, relative max, maximus. Okay, and relative mean. Let's see what we got. Ba-da-ba-ba-ba. Oh boy. Identify the location of the value of any relative maximum. The point. Oh, this first one that wants a minimum. Second one is a maximum. Where's my min? What point? I think right here. That's a min. 1, 2. So negative, the point -2, -1 is the lowest point in a small interval surrounding x equals -2. So at x equals -2, the function has a relative min of -1. Looks like it has a max right here at the point 0, 1 is the highest point in the small interval surrounding x equals 0. So at x equals 0, the function has a relative max of 1. It's not so bad. That's not so bad. In fact, I'm going to work ahead. You're going to work ahead, and you're going to chop that up. Looks like I have a min, a max, and another min. So let's see, this is asking for a min, and then the max. So my first min is going to be at x equals -1. That's here. It has a minimum of -2. Here's another minimum. At x equals 4, it has a relative min of 0. Max, see how I said that in a deeper voice. Max at x equals 2, the function has a relative maximum of 3. Uh-oh, there's no wording over here. There is no max. There is no min. For my calc students, this has a reflection at 0, 0. It's called a reflection. I go from something called concave down to concave up. You don't need to worry about that. But that's something coming up in the future. Ta-da! I'm going to stop the recording. That's the lecture for today.